Hi again. In this video, we're going to talk about z-scores. So we were just looking at z-scores because that is an output of Staplett when we're finding a probability. So we're going to see what those mean. And we also looked at them earlier in the course when we were doing descriptive statistics. We computed a z-score to compare an individual to the group. So if you have a data set, you've got a mean and a standard deviation, you can figure out how many standard deviations away from the mean is a particular individual. Okay, so we did that, and now we're going to see we can also use them to compare unlike events. Okay, also this comparison does make a little more sense when it's a symmetric distribution, just because it wouldn't necessarily be the same on both sides if it's not symmetric. Okay, so here's an example. We're going to continue with the rainfall and then add on to that. Okay, so we've got our rainfall example we've been working with. Assume the average annual rainfall in Portland is 40 inches a year with a standard deviation of 8 inches. Okay, so we've got rainfall in Portland, 40 and 8. Also assume that the average wind speed in Chicago is 10 miles per hour with a standard deviation of 2 miles per hour. Okay, suppose that 1 year's Portland in 1 year, Portland's annual rainfall was only 24 inches and Chicago's average wind speed was 13 miles per hour. Which of these events was more extraordinary? Okay, so just comparing the 13 with the 10 and 2 and the 24 with the 40 and 8, I can't really tell what's going on, That's why a picture or a z-score is so helpful. So here's our z-score formula. And when we looked at it before, we were doing descriptive statistics. So you probably saw it in this form, z equals x minus x bar over s, because those were our sample statistics. But now when we're in a theoretical model, we use the Greek letters, the parameters. Okay, I think I also wrote it out in words too, that x minus the mean divided by the standard deviation. Okay, so let's try this, and I'm also going to define, just because it's good practice, and it also just helps me pull the right numbers out of the paragraph. So I'm going to define each distribution. So I'm going to say x for Portland, so x sub p, except I was doing those in green. X sub p is distributed as a normal distribution with a mean of 40, comma, standard deviation of 8. Okay, and then our z-score formula will be our particular x value, so that's 24. We always put that first. 24 minus the mean of 40 divided by 8. Okay, so let's see what this comes out to be. 24 minus 40 is negative 16. Okay, so that tells me that year had 16 inches below normal. So that's pretty dry, but I still don't know exactly how it compares to everything else, all the other years. So 16 divided by 8 then, I think I can do that in my head. It's negative 16 divided by 8 is negative 2. So that means it's 2 standard deviations below the mean. Okay, and I can actually verify that because when we made our drawing, remember how we put 40 in the middle and we went down by the standard deviation? So z-score of 1 would be minus 1 would be 32, minus 2 is 24, minus 3 is 16. Okay, so it checks out. And then our units are standard deviations. Okay, now let's do a z-score for the wind speed. So first let's write x sub c for Chicago is distributed normally with a wind speed, an average of 10 and a standard deviation of 2. Okay, so same idea. We're going to take our x value, which is the individual one that we're trying to find the z-score of, 13, minus our mean, which is 10, divided by our standard deviation, which is 2. Okay, this one I can do 13 minus 10 is 3, divided by 2, and I know that's 1.5, but I'll do it as well. 13 minus 10. I need to hit enter and divide by 2 next. Or you could put parentheses around the top. I could do parenthesis 13 minus 10, close parenthesis, divided by 2. You could do that as well. I get 1.5. But notice if I do 13 minus 10 divided by 2 without any parentheses, I get 8. So if you get something that seems off, double check your order of operations. So this is doing division first, so it's actually doing 13 minus 5. That's not what we want. Okay, so the wind speed is 1.5 standard deviations. And that's above the mean because it's positive, right? Okay, so how can we, which one was more extraordinary? If only we had a graph to show this on. Just happen to have one down below, so I'll come back to that answer in just a second. If we were to make a graph of all these z-scores, and that's called the standard normal model, it has a mean of 0 because you see how we subtract the mean? We subtract the mean. So if we put the mean, the exact value for the mean in there, the mean minus the mean would be 0. So it's always centered, z-scores are always centered at 0. And then 1 means 1 standard deviation above the mean. And 2 means 2, and 3 means 3 standard deviations above the mean. And then for z-scores, we'll have negatives on the left side because -1 means 1 standard deviation below the mean. -2 means 2 below, and -3 means 3 below. Okay, so to define our standard normal, it's written here, but I'm just going to write it out again. We use the letter Z, and that's for the z-score. But whenever you see the letter Z, that tells you it's a standard normal, okay? So that letter is reserved for the standard normal distribution. So Z is normal with a mean of 0 and a standard deviation of 1, okay? Except for Stat 243Z, that Z is for Common Course numbering throughout the state of Oregon. That's a different Z, but also a Z. Okay, so then I could just write z-scores for my scale, or I could write the number of standard deviations. Okay, so let's go ahead and mark. Let me back up here for a second and take, so Portland is -2, so that's 2 standard deviations below the mean. So that's where the Portland rain was, or lack of rain. And then the Chicago was 1.5. That was the Chicago wind. Okay, you could probably tell from the numbers that -2 is further away from 0 than Chicago, right? But it also helps to see it on a graph. I'll put a green dot here as well. Okay, so I'm going to go back up and write our answer to that one. That between these two events, the Portland rain of only 24 inches is more extraordinary. The Portland rainfall, I forgot to capitalize my P. The Portland rainfall of 24 inches is more extraordinary. That's spelled extraordinary. Because it's z-score. How do I want to say that? It's further from the mean. Its z-score shows it's further from the mean. Its mean, really, because there's two different means, right? Okay, or in another case, they might give you two things you're comparing and they want to know which one is better. So it might be that the higher one is the better one, right? So it depends on the wording in the question, what you're looking for. This one, more extraordinary, means further away, because the further away you get out on this normal curve, the further out you get away, the less chance there is of that happening, right? And we know if it's between 2 and 3, that's getting unlikely, and if beyond 3 is pretty rare. Okay, so we can also find probabilities regarding z-scores. So here's a couple of examples, and we're going to go ahead and use Staplet for that. So these are already written in the probability statement, so I don't need to write a probability statement, but it could be written in words as well. So let's go to Staplet, and now this is a new model. So I'm going to go back up to my mean and put in 0 for that, and 1 for my standard deviation. And now I have the picture that matches our standard normal, right? 0, 1, 2, 3, -1, -2, -3. And I want below, to the left, below 1.5. So what's the chance of getting a value that's below 1.5 standard deviations above the mean? Okay. Turns out that is 0.9332. And look how it says z equals 1.5. So it just gives us a z-score, that value. It's a little bit redundant on the standard normal. But that's okay. It's very helpful, I think, on the other ones. So that is, oops, I forgot already, 0.9332. Okay, wow, that's a lot. So that's 93%, and there's only 7%-ish in that tail. Okay, let me look at the next one. Okay, and remember, some of these will be negative because you can have a negative z-score. So from -0.3 up to 0.5, so that's kind of central. Let me type that in. Same mean, same standard deviation. This time we're going between. And notice there's a z in these probability statements. So -0.3 up to 0.5. Okay, yep, it's a pretty narrow little area, isn't it? And it's an area of 0.3094. Okay, 0.3094. Okay, so now you can find a z-score, and you can also find the probability for anything in the standard normal model. Okay, great. That does it for z-scores, and I'll see you in the next video.